Let us look at the balanced chemical equation for the reaction between nitrogen and hydrogen in the synthesis of ammonia. Now, what do we understand from this equation? Obviously, we understand that two elements, namely nitrogen and hydrogen, are reacting with one another to form a single compound called ammonia. What else do we understand from this equation? Remember, by convention, this formula N2 represents one molecule of nitrogen. This represents one molecule of hydrogen and this one molecule of ammonia. And you can also see some coefficients before these formulae. And if you don't see a number before a formula or a symbol, that means there is a 1 there. And these coefficients that you see in a balanced chemical equation are known as stoichiometric coefficients. Now, what do they tell us? They tell the number of molecules of each type that completely react with one another and the number of molecules of product formed during that reaction. So, in this case, we understand that one molecule of nitrogen completely combines with 3 molecules of hydrogen to form 2 molecules of ammonia. But does it mean that we have to carry out the chemical reaction only between 1 molecule of nitrogen and 3 molecules of hydrogen? So this equation is not saying that every time you carry out a chemical reaction between nitrogen and hydrogen, you can combine only 1 molecule of nitrogen with 3 molecules of hydrogen. That does not make sense. We carry out chemical reaction between a sample of nitrogen containing a large molecules of nitrogen and a sample of hydrogen containing a large molecules of hydrogen. Then what do we understand from these coefficients? These coefficients tell us that for every molecule of nitrogen, there must be 3 molecules of hydrogen. That is what these coefficients indicate. So my question is, if you want to carry out this chemical reaction efficiently, that is without leaving any unreacted hydrogen or nitrogen, then in what proportion should nitrogen and hydrogen be mixed? Can you answer that question by looking at this equation? Of course, we can answer that question. From these stoichiometric coefficients, we understand that each molecule of nitrogen completely combines with 3 molecules of hydrogen. So, if the number of molecules of nitrogen and hydrogen in the samples that you are combining are in the ratio of 1 to 3 respectively, then all the nitrogen and hydrogen that you took will completely combine with one another to form ammonia without leaving any leftovers, assuming the reaction goes to completion. So our question is answered, right? Every time you carry out this particular reaction, if you make sure that the nitrogen and hydrogen molecules are in the ratio of 1 to 3 respectively, then there will be no leftovers. All the nitrogen and hydrogen that you took will be converted completely into ammonia, assuming that the reaction goes to completion. Now let us say I have some pure nitrogen in a box and I want to convert all this nitrogen into ammonia. How can I do that? How much hydrogen do I need? Here is the formula. If you make sure that their molecules are in the ratio of 1 to 3, then we are good. So to be able to do that, first you have to count the number of nitrogen molecules present in this cylinder, right? Then take 3 times as many hydrogen molecules, then you are good. But the problem here is, how do you count the number of nitrogen molecules present in this container? Molecules are extremely tiny particles. Can you do that? No, it doesn't make sense. So this balanced chemical equation tells me the relative number of particles, in this case molecules, that are completely reacting with one another. And to mix these particles in this proportion, I should be able to count the number of particles present in the samples I have taken. But I cannot count the number of particles, atoms or molecules or ions in any sample. That is almost impossible. So I have a problem. This equation tells the relative proportion of the particles that are completely combining with one another, but I cannot count the number of particles present in any sample. Then how do I overcome this difficulty? But don't worry, there is a workaround. That is, we can combine nitrogen and hydrogen molecules in this ratio without having to count directly the nitrogen and hydrogen molecules. Interesting. How can we do that? Just for the sake of our discussion, imagine that we have one nitrogen molecule with us. And to completely combine with one nitrogen molecule, we need 3 hydrogen molecules. That is what this equation tells. Now, what is the mass of nitrogen we have? You know, the molecular mass of nitrogen is 28U. You know how to figure this out. Check out the previous video. That is, one molecule of nitrogen weighs 28U. And we have one nitrogen molecule with us. So the total mass of nitrogen is 1 times 28U. And the molecular mass of hydrogen is 2U, and we have 3 such hydrogen molecules. So this is the total mass of hydrogen that we have. Then what is the ratio between their masses? See, these 2 U's get cancelled, then the ratio becomes 28 to 3 times 2, or 28 to 6. Now let us say I have 2 nitrogen molecules, and to completely combine with 2 nitrogen molecules, we need 6 hydrogen molecules. Their numbers must be in the ratio of 1 to 3. 2 to 6 is 1 to 3, right? Then what is the total mass of nitrogen we have? Again, it is 2 times 28U, and the total mass of hydrogen we have is 6 times 2U. Again, the ratio becomes 28 to 3 times 2, or 28 to 6. Now in general, if you have N nitrogen molecules, then you need 3N hydrogen molecules. Again, the ratio of their molecules is 1 to 3. N to 3N is 1 to 3. Then what is the total mass of nitrogen we have? Again, N times 28U, and the total mass of hydrogen becomes 3N times 2U. Again, the ratio is 28 to 3 times 2, or 28 to 6. So in all these instances, the nitrogen and hydrogen molecules are in the ratio of 1 to 3. And if you look at the ratio of their masses, interestingly, and of course obviously, it is the same. In each of these cases, it is 28 to 6. Now, what did we understand from this? What we understood from this is, if the nitrogen and hydrogen molecules are in the ratio of 1 to 3 in the samples of nitrogen and hydrogen that we took respectively, then their masses are always in the ratio of 28 to 6. Then is the converse also true? That is, if the masses of the samples of nitrogen and hydrogen that we took are in the ratio of 28 to 6, then are their molecules in the ratio of 1 to 3? Of course. So, if you take nitrogen and hydrogen so that their masses are in the ratio of 28 to 6, then you are guaranteed to have their molecules in the ratio of 1 to 3. So that means we are able to pick samples of nitrogen and hydrogen so that their molecules are in the ratio of 1 to 3 without actually counting the molecules. How did we do that? Just by making sure that their masses are in the ratio of 28 to 6. Can you measure masses? Of course. We can very easily and accurately measure masses. So, by using this workaround, we are able to achieve what we wanted to do. That is, combine nitrogen and hydrogen molecules in the ratio of 1 to 3 without actually counting the molecules. Now let us say I have 28 grams of nitrogen with me, and to completely combine with this much of nitrogen, what is the mass of hydrogen required? From this we understand that we need 3 times 2 grams of hydrogen. Now if you look at the ratio of their masses, it is again 28 to 6. That means we have nitrogen and hydrogen molecules in the ratio of 1 to 3. So we are good. Now what is 28? It is the molecular weight of nitrogen, and to it we simply added the unit gram. If you express molecular weight in grams, it is called gram molecular weight. See, molecular weight is 28, and if you add gram to the right hand side, you have to add the word gram to the left hand side to create a name for this quantity. So that is why it is called gram molecular weight, or it is also known as gram molecule or gram mole or simply mole. So that means if you have 28 grams of nitrogen with you, you have 1 mole of nitrogen. Similarly, molecular weight of hydrogen is 2. So 2 grams of hydrogen by the same logic is simply 1 mole of hydrogen. So, or in other words, 1 mole of nitrogen completely combines with 3 moles of hydrogen. And if you look at the ratio of the number of moles, it is again 1 to 3. So the ratio of the number of molecules is 1 to 3, and the ratio of the number of moles is also 1 to 3. So without entering a laboratory, sitting at your home, if you want to calculate the amounts in which various reactants must be combined to carry out a particular chemical reaction without any wastages, you need the balanced chemical equation for that reaction. From the balanced chemical equation, you can figure out the ratio of the number of particles that are completely combining with one another. And if you ensure that the particles are in that ratio in the samples that you are combining with one another, then there will be no wastages. But because you cannot directly count the number of particles, we are taking the help of their masses, and in some cases we take the help of their volumes to indirectly figure out the number of particles present in them. So, for this reason, you must learn how to figure out the number of particles present in a sample given its mass or its volume. Remember, chemical reactions always take place between particles, atoms, molecules, ions, etc. Therefore, you always have to think in terms of the number of particles. To be able to do that, you should know how to convert masses and volumes into number of particles. And that is what we are going to do in this video. In chemical reactions, we generally come across atoms, molecules, and ions, and the formula of an ionic compound is called its formula unit. And for an atom, we have defined something called its atomic weight, also known as relative atomic mass. And for a molecule, molecular weight, also known as relative molecular mass. And for a formula unit, formula weight, also known as relative formula mass. And for an ion, ionic weight or relative ionic mass. I have explained these terms in a previous video, and if you want, you can go back and watch it. If you express the atomic weight of an element in grams, it is called its gram atomic weight or simply gram atom. If you express the molecular weight of a molecular substance in grams, it is called gram molecular weight, gram molecule, or gram mole or mole. So many names for the same thing. And if you express the formula weight of an ionic compound in grams, it is called its gram formula weight. Similarly, if you express the ionic weight of an ion in grams, it is called its gram ionic weight or simply gram ion. And 1 gram atom of any element contains an Avogadro's number of atoms. 1 mole of any molecular substance contains an Avogadro's number of molecules. 1 gram formula weight of any ionic compound contains an Avogadro's number of formula units, and 1 gram ion of any ion contains an Avogadro's number of ions. Though we have different names for different types of particles, they all contain the same number of particles. The good thing with these names is there is no confusion with these names. If I say gram atom, you understand that I am talking about atoms. If I say mole, you understand that I am talking about molecules. And if I say gram ion, you understand that I am talking about ions. But they all contain the same number of particles. For this reason, they thought of replacing all these names with a single name, that is mole. This is replaced with the name mole, and this also is replaced with mole. So, what is 1 mole of atoms? It contains an Avogadro's number of atoms, and its mass is equal to its atomic weight in grams. Now, what is 1 mole of molecules? It contains an Avogadro's number of molecules, and its mass is equal to its molecular weight in grams. What is 1 mole of an ionic compound? It contains an Avogadro's number of formula units and its mass is equal to its formula weight in grams. Then what is 1 mole of ions? It contains an Avogadro's number of ions and its mass is equal to its ionic weight in grams. So we use the same name mole for all types of particles, and you can extend this definition for any other type of particle like electron, proton, neutron, etc. Now let me repeat. 1 mole of an atomic substance contains an Avogadro's number of atoms and its mass is equal to its atomic weight in grams. 1 mole of a molecular substance contains an Avogadro's number of molecules and its mass is equal to its molecular weight in grams. 1 mole of an ionic compound contains an Avogadro's number of formula units and its mass is equal to its formula weight in grams. And 1 mole of any ion contains an Avogadro's number of ions and its mass is equal to its ionic weight in grams. Now let us look at these terms: number of gram atoms, number of moles, number of gram formula weights and number of gram ions. Now going by these old names, what is 1 gram atomic weight of an element? 1 gram atomic weight of an element is nothing but its relative atomic mass or atomic weight in grams. Or in other words, if you have AR grams of an element, that means you have 1 gram atom of that element. Now say you took m grams of that element, then how many gram atoms do you have? See, the number of gram atoms, number of moles and all these things are represented by the symbol small n. Then the number of gram atoms or small n will be equal to, you have to multiply these two terms and divide that product with this one. So it becomes m grams multiplied with 1 over AR grams. That becomes m grams over, what is AR grams? It is nothing but its gram atomic weight of an element in grams. So m grams over gram atomic weight. That is what I have written here. This is the expression for the number of gram atoms going by the old names. By using a similar argument, you can derive an expression for the number of moles also. It is equal to mass of the substance given in grams over its gram molecular weight. And similarly, these are the expressions for number of gram formula weights and number of gram ions. But now we have replaced all these names with mole. So you have to replace this with mole, this also with mole, this also with mole and this also with mole. Again, gram atoms are replaced with the name mole. Gram formula weights are also replaced with the name mole. Again, this also replaced with mole. So all we have now is number of moles. So instead of having different names and expressions for each type of particle, we can have a single name and a single expression for all types of particles, and that is number of moles. And it is given by the ratio between mass of the substance given in grams and mole. Now what is 1 mole or what is mole? It depends on the type of particles that we are talking about. If you are talking about atoms, then it is its relative atomic mass in grams. If you are talking about molecules, then it is relative molecular mass in grams. If you are talking about an ionic compound, you are talking about its relative formula mass in grams. And if you are talking about an ion, then it is relative ionic mass in grams, and you can extend this to any other type of particle. So in general, mole can be defined for any particle as its relative mass expressed in grams. That is what we have here, right? For atoms, it is its relative atomic mass in grams. For molecules, relative molecular mass in grams, and so on. So that is what I have written here. So number of moles for any type of particles is mass of the substance given in grams over the relative mass of that particle expressed in grams. So far, so good. And everything was going more or less okay until the year 1972. In the year 1972, they have added a new fundamental physical quantity called amount of substance to the SI system. See, to represent the amount of matter present in an object, we already have a fundamental physical quantity called mass. If an object has more matter, it has more mass. But there is no fundamental physical quantity to represent the number of particles present in a system, like the number of atoms present in an iron bar, or the number of molecules present in a nitrogen gas cylinder, and so on. So for this reason, in the year 1972, to represent the number of particles present in a system, they have added a new fundamental physical quantity called amount of substance. And if you have more particles in the system, that means the amount of substance is more. If there are less particles, the amount of substance is less. Now, every fundamental physical quantity, or for that matter, every physical quantity, must have a unit. For mass, the unit is kilogram. Now, if amount of substance is a fundamental physical quantity or a physical quantity, it also must have a unit. Quite surprisingly, they gave the name mole for the unit of amount of substance. So after 1972, mole has an entirely different meaning. It is simply the unit of the fundamental physical quantity amount of substance. Before 1972, mole represented certain mass of the substance. 1 mole of an atomic substance is equal to its atomic weight in grams. So 1 mole of sodium atoms means 23 grams, or 1 mole of oxygen molecules means 32 grams of oxygen, and so on. So before 1972, mole means certain amount or certain mass of the substance. But after 72, mole is the unit of the fundamental physical quantity called amount of substance. Its meaning has been changed entirely, and this is very confusing. Now, to make our lives easier, we can compare amount of substance with something that we already know. Amount of substance is nothing but number of moles, loosely speaking. So wherever you see number of moles in your textbook, you can simply replace it with amount of substance without changing its meaning. But there is one big difference. Number of moles, because it's a number, it is dimensionless. It is simply a number without any units. But amount of substance is a physical quantity and its unit is mole. And the symbol for this unit is MOL without the E in the end. So amount of substance must always be expressed in those units. It has to be 2 mole or 7 mole and so on. So don't forget about this unit. Now, given the mass of the substance in grams, how do you find out the number of moles? You divide the given mass in grams with mole, that is the relative mass of the particles expressed in grams. Similarly, to get the amount of substance, you have to divide the given mass in grams with what is called molar mass. What is molar mass? By definition, molar mass is the mass per 1 mole of the substance. And again, by definition, 1 mole of any substance contains an Avogadro's constant of particles, to be precise. And Avogadro's constant is represented by Na. And Avogadro's number is represented by N. There is a small difference between these two. I will explain that shortly. And we have picked the value of Avogadro's constant in such a way that the mass of those many particles will be simply equal to the relative mass of the particle in grams. So the mass of an Avogadro's constant of atoms is simply equal to its relative atomic mass in grams. The mass of an Avogadro's constant of molecules is simply equal to its relative molecular mass in grams, and so on. So molar mass is therefore relative mass of the particle expressed in grams per mole. Remember, here we have to keep the unit mole. And here mass is in grams and the quantity in the denominator has the unit mole. So the unit of molar mass is gram per mole. So molar mass is nothing but the relative mass of the particle expressed in gram per mole, and amount of substance given the mass of the substance in grams is the given mass in grams over molar mass. Now we are ready to work out some examples. By the way, what is the difference between Avogadro's constant and Avogadro's number? Avogadro's constant and Avogadro's number are numerically equal. But the difference is that Avogadro's constant has the unit per mole. So Na, that is Avogadro's constant, is equal to Avogadro's number expressed in the unit per mole. And what is the value of Avogadro's number? It is approximately 6.022 into 10 to the power of 23. Then what is Avogadro's constant? The same number, 6.022 into 10 to the power of 23, but with the unit per mole. So pay attention to this difference. When you are working with amount of substance, you have to use Avogadro's constant to figure out the number of particles. If you are working with number of moles, that is the old vocabulary, you can use Avogadro's number. Now you will understand this better when we start working out some examples. Now in this question, we are asked to calculate the amount of substance or the number of moles in each of the following cases. And if you want to use the old vocabulary, number of gram atoms or number of gram atomic weights. In the first case, we are given 0.23 grams of sodium and the atomic weight of sodium is given as 23. Now, how do you get the number of gram atoms? Do you remember the formula? You have to divide the mass of the element given in grams with its gram atomic weight. What is the mass of the element given in grams? 0.23. And if the atomic weight of sodium is 23, its gram atomic weight is 23 grams. Cancel these units, then it becomes 1 over 100 or 0.01. But I think I can add a trailing 0 here. Why did I do that? It has something to do with significant figures. You figure that out. So the number of gram atoms of sodium in 0.23 grams of sodium is 0.010, or you can also express it in exponential form as 1.0 times 10 to the power of minus 2. See, number of gram atoms is just a number. Now, how do you get the number of moles of sodium atoms? Now, what is the formula for the number of moles? It is mass given in grams over the relative mass of the particle expressed in grams. What is the mass given in grams? Again, I will write it here. Mass given over relative mass of the particle in grams. What is the mass given? 0.23 grams. And what are the particles we are talking about? Sodium atoms. What is the relative mass of a sodium atom? 23. If it is expressed in grams, it becomes 23 grams. Again, it is 1 over 100 or 1.0 times 10 to the power of minus 2. Then how do you get the amount of substance? It is mass of the element given in grams over the molar mass of that element, whatever that element is. What is the mass given? 0.23 grams. And what is the molar mass? Here we are talking about sodium atoms, and its atomic weight is 23. So molar mass of sodium atoms is 23 grams per mole. Cancel these two units, then it again becomes 1 over 100, but now this has the unit mole. So it is 1.0 times 10 to the power of minus 2 mole. So see the difference? Number of moles is a number, whereas amount of substance has the unit mole. Now let us work out another example. 3.2 kilograms of sulfur. Now how do you get the number of gram atoms? Mass of the element given in grams over its gram atomic weight. What is the mass of the element given in grams? 3.2 kilograms. Pay attention to this. But we have to use it in grams. So first you have to convert that into grams. You know 1 kilogram is equal to 10 to the power of 3 grams. So 3.2 kilograms would be 3.2 times 10 to the power of 3 grams. So 3.2 times 10 to the power of 3 grams over the atomic weight of sulfur is 32. So its gram atomic weight would be 32 grams. Cancel these units and simplify this. I will leave the simplification to you. Don't ignore significant figures. Then how do you get the number of moles of sulfur atoms? Remember, sulfur is generally composed of sulfur molecules, but here I am looking for the number of moles of sulfur atoms, not sulfur molecules. Then what is the formula? Mass of the element given in grams over the relative mass of the particle in grams. What is the mass of sulfur? 3.2 into 10 to the power of 3 grams over What is the relative mass of sulfur atom? 32 grams. So it is again same as the number of gram atoms. You do the simplification. Then how do you get the amount of substance of sulfur atoms? Remember, I am not talking about sulfur molecules, I am talking about sulfur atoms. It is simply mass of the element given in grams over the molar mass of sulfur, right? Sulfur atoms to be precise. The mass of sulfur given is 3.2 into 10 to the power of 3 grams. Then what is the molar mass of sulfur atoms? It is equal to its relative atomic mass in grams per mole. If you are talking about atoms, then the molar mass is its relative atomic mass in grams. Relative atomic mass of sulfur is 32, so 32 grams per mole. Cancel these two units, simplify this, but remember the answer will have a unit, so don't forget that unit. So now that you understand how to calculate the number of gram atoms, number of moles and amount of substance, I will leave the remaining as an exercise for you.